So what the CBFS really is? The CBFS stands for Core Boot File System. It has a similar concept to file system, but in fact it is not one of them. It's rather a scheme for managing independent binary data, so-called files, located in a single RAM image. It is meant to be flashed on RAM chips. Its main property is that it's read-only. It shall be assembled off-target from some data chunks into a single ROM image. Then it can be flashed on a target RAM chip. Utility that is capable of assembling such image is called CBFS tool, and will be discussed in next lesson. Also, there is no such thing as directory structure, even when sometimes it may look like this.
What actually is a CBFS tool? CBFS tool is an utility for managing CBFS formatted ROM images. It is used in Core Boot build process to assemble a ROM image structure, but it can also be used manually to print image structure, add a new file, or extract an existing one. It is built as a part of the Core Boot build process and finally located at build CBFS tool. The source code, however, lies in the util CBFS tool. So let's have a quick look how it does look like after the build process. So here, when the build finishes, the CBFS tool prints the default flash map region, which is called Core Boot. Typical builds contain only the Core Boot region, but if we have vboot, we can have multiple CBFS regions, and they are all printed at the end of the build. So the basic output of the print command, which displays the CBFS structure, contains a few columns: name, offset, type, size, and compression. In the name column, we of course have the file name under which the file resides. So actually we have various files like CBFS master header, which contains some basic information about this CBFS region, the ROM stage, RAM stage. We have also some basic Core Boot files like its minimal configuration, revision. We have the DSDT ACPI table. We have the CMOS layout configuration file for the runtime configuration. We have some payload configuration, and always the boot block, which lies at the end of CBFS. The offset column indicates the hexadecimal offset from the beginning of the CBFS at which the file is located. And the type column indicates what kind of file it is. It may be a CBFS header, which is reserved only for the CBFS master header, and we have various types like stages, which are the Core Boot executable stages. You can have raw files, which doesn't have any predefined format inside. You can have the CMOS layout has its own type. The serial present detect, the SPD data, which is used in the memory training and the D modules, have also its own type. The Intel FSP has its own type, and we have also a simple ELF file as well for the payload, and bootlog has its also own type. The size column represents the size of a given file in bytes. These files are in decimal format. And the compression column indicates whether any compression has been applied to a given file. Although payload and run stage is compressed by default, there is some bug in this tool which doesn't state any compression applied to these files, although in fact there is a compression. So basically, if there is a compression applied here, for example, VBT files are often compressed with LZMA, it will indicate it is LZMA. Recent Core Boot also allows to compress the FSPS images with LZ4, and it also will state that the FSPS is compressed with LZ4. Okay, now let's review the CBFS tool utility command line. As I mentioned earlier, the CBFS tool after the build process is located at build/CBFS tool. It has a really good command line help, so All possible comments, parameters, and types can be found directly there. The syntax is quite simple. It just requires us to pass the ROM image file path as the first argument, then the desired comment, and the parameters at the end. The -v flag can of course be used for additional verbose output. The most commonly used comments are probably the print, extract, add stage, add payload. So let's review how the help looks like. So here we have after the build process, and we can just execute the build CBFS tool, and it printed us the help and the usage. So as I already presented you, here is the example of usages. And here we have the short explanation of various options that can be applied as well. And the most important are the commands. So the first command is add, and it simply allows us to add a file to the CBFS. One can point to the region or the flash map region where the CBFS lies. Note that only the regions which are of CBFS type or contain a CBFS can be used here. The -f allows us to pass the file path of the file that should be included, -n to define the name, and -t to define the type. Optionally, we may append a hash to the CBFS file and have it printed on the standard output. And there are various various algorithms that can be used. -c is for optional compression, -b is for the base address, and -a is for the alignment in the CBFS. But the base address and alignment are mutually exclusive, so only one can be used at a time. We can also define some additional padding size to align the end of the file, or we may additionally indicate whether this image is executed in place. This is especially useful for early stages that execute from caches RAM or FSP. We can also define some top swap size, so it cooperates with the top swap mechanism on Intel CPUs. And we can also define additional algorithm, which is IBB. This indicates that the given file is a component of the initial boot block, which is very useful when implementing bootguard or TXT. We may also add a payload with the command added payload. Basically, its syntax is similar to add command. However, it may contain some various payload specific options, like for example for Linux we can have additional command line and initial RAM disk. Add stage is basically used for the core boot stages only. So there is an optional parameter uppercase S, for example, to ignore certain ELF sections. This is especially useful when including some execute in place files, and some certain sections are ignored because they do not make any sense in cache-SAM environment. We can also add a flat binary, which is a 32-bit flat mode binary. And you can define the load address and entry point of the. We have to actually pass the load address and entry point of this binary. We can add a simple 64-bit integer to the CBFS. This is especially useful with, for example, with CBIOS configuration. We may just include an integer with an appropriate name to make changes to the CBIOS behavior without recompiling it. There's an option also to add the CBFS master header. We can also remove a given file from given region. You can compact the given image. So for example, if we have some read-write partitions in the flash map, which contains CBFS, we may truncate the CBFS at the end of all added operations to just defragment this image and remove all unused space. We can also copy or duplicate a given CBFS image from one partition to the second one. We may also create a legacy ROM file with CBFS master header. We can locate a given or actually we can find a place for a file of given size and given region. We can produce a layout from the CBFS image. This layout is especially useful when we want to know how the flash map regions are actually spread across the whole image. We can print this whole image, which I already described in previous slides. We can extract certain files. We can write to the flash map regions. So basically, what it allows us to write raw data to the raw region without any CBFS structure. And here we can define the file which should be written, and whether it should be written upside down or downside up. Or we can even write it with some kind of integer to fill the free space. We can also read a given flash map region, so basically we save a region contents to a file. We can truncate the CBFS and print its new size to the standard output, and we may of course expand the truncated CBFS to span the entire flash map region. Also, you can see here how the specific arguments are defined, what are the possible values, and what is their format. For example, we have architectures which are possible to pass and which CBFS understands, and what kind of file types one may use when adding or extracting a file or modifying the file.